Alright, in this video we'll be going through the first question of the 2012 past paper. I thought this was a pretty good question that applies internal resistance, so we can go through it today. So it says that Hugo has bought a remote controlled car. He removes the battery from the car and connects it to a variable load that allows him to control the current. Okay, and so that is this situation right here. If you have watched my first video on internal resistance, you should remember this circuit setup. Okay, this is towards the end of the video. And the circuit setup just allows us to plot a graph with the voltage on the y-axis and the current on the x-axis, okay? And this is done by changing this resistor here. This is a variable resistor, so we change the resistor values and we get different voltage and current values out of it, okay? So part A wants us to calculate the size of the resistance that Hugo uses to draw a current of 500 milliamps, all right? So if we look at our graph, we can see that this right here is 500 milliamps, and if we go up, we can see that we get 6.2 volts, okay? And so therefore, we know our current is obviously 0.5 amps, and our voltage is 6.2 volts, and so therefore, as V is equal to IR, and therefore R is equal to V all over I, we get 6.2 all over 0.5, and we get 12.4 ohms. There we go. Use your graph to estimate the EMF of the battery. So again, if you've watched my first video on internal resistance, this should be pretty simple, okay? But if you haven't, well, we can go through it now. We can see here that this is obviously the power supply, okay? And the power supply has an internal resistance. If we think about this, let's say the power supply is going to provide an EMF, okay? And then as the current flows through the circuit, a voltage value that's equal to the current multiplied by the internal resistance, which we can denote as little r, is going to be taken off. And then as the current comes through here, another voltage value that's equal to the current once more, times the external resistance, which we can denote as capital R, is also going to be taken off. And so therefore, our EMF, minus the voltage drop due to our internal resistance, minus our voltage drop due to our external resistance, is going to equal to 0, okay? And we know it needs to equal to 0 due to Kirchhoff's voltage law. Therefore, we can write this as our voltage drop due to our external resistance is equal to negative IR plus EMF, okay? If we look over here, just erase this for a second. If we were to put a voltmeter across this external resistor, we can see that the voltage measured across this external resistor is going to be equal to the voltage read across our power supply. The reason for that goes back to our definition of what it means for components to be in parallel. We can see this side of the top voltmeter shares a node with this side of the bottom voltmeter, and this side of the top voltmeter shares a node with this side of the bottom voltmeter, okay? And so therefore, as both voltmeters share a node on both of their ends, therefore they are in parallel, and so they have the exact same resistance because the potential difference on both sides is the same. And so if the voltage drop for this external resistor is equal to our terminal voltage, that means our terminal voltage, which we can denote as V, is equal to negative Ri plus our EMF, okay? Now, if I were to just move this equation, we can see that this equation resembles y is equal to mx plus c, okay? Where our voltage is our y-axis, okay? And you can see that over here, we can see our voltage is our y-axis, okay? And our current is our x-axis, which we can see here, our current is our x-axis, okay? And so that means that our internal resistance is equal to our gradient, okay? And so the gradient of this graph is our internal resistance. But more importantly for this question, that means that our EMF is the y-intercept, okay? And so does that make sense? Well, if we think about it, our EMF is the total possible voltage when no current is flowing. And so our y-intercept is when our x value is equal to 0, and we know our x-axis measures current. And so when our current is equal to 0, that voltage value is our EMF, right? And so simply, in order to find that, we need to estimate that, and so we can just backtrack this line, okay? And we should get roughly 7.4-ish. And in terms of explaining your answer, you can explain what I just explained. Okay, use the graph to calculate the internal resistance of the battery. Well, like I just said before, our internal resistance is equal to the gradient of the graph. And so therefore we can calculate our gradient. We can grab our 2 points. We go from 7.2 all the way to 5.8, I believe. Okay, so our internal resistance is equal to rise all over our run. And our rise is from 7.2 minus 5.8. And so our 7.2 value has a current of 100 milliamps. Okay, minus our 5.8 value, which has a current of 700 milliamps, alright? And this equals to negative 2.33 ohms. And therefore our internal resistance is equal to 2.33 ohms, okay? And obviously, to explain our answer, we know that from Kirchhoff's voltage law, we get this relationship right here, and we can see that our internal resistance is the negative of the gradient. When we calculate our gradient, we get negative 2.33, and so our R value is 2.33. Hugo puts the battery in the car and plays with the car until it's running noticeably slower. He removes the battery again and repeats the experiment, measuring the terminal potential difference and the current. Draw a line on a graph to show the relationship between the terminal potential difference and the current from this used battery, and explain why you have placed the line where you have. Okay, so again, if you've watched my first video on internal resistance, you should know that when we use our supply, so our power supply, in this case a battery, our internal resistance is going to increase, okay? And in that video, I said it's something to do with the buildup of chemicals. It's like a chemistry thing, you know, if you've done redox, then you should know. But if you want a summary, it's to do with the buildup of like a solid on the cathode and anode, okay? And that's just to precipitate from when the chemical reactions take place, okay? And so that just causes the resistance to increase. But as we know, our EMF still remains the same, okay? So that's constant, okay? But if we look at our equation, this equation right here, where we will have our terminal voltage is equal to our negative IR plus our EMF, okay? So if our EMF is constant, then our y-intercept on the graph is going to remain the same, alright? But our R value is getting bigger and bigger, and so our gradient is going to be steeper, alright? And so if our gradient is steeper, but our y-intercept is the same, we're gonna have our y-intercept right here, and we're gonna go down like so. That should be a straight line, like that. Again, it doesn't need to be perfect values because we're not given values, it just needs to be for illustration purposes. It just needs to be a steeper graph, okay? And so that is it for this question, alright? As you can see, this is a nice question that applies a lot of the concepts for internal resistance, especially when it comes to this situation of plotting voltage over current and using this circuit right here, alright? See you.